Official members bounce, bust off the chrome. Realize it's real hell, what we call home.
Official members bounce, bust off the chrome. Realize it's real hell, what we call
From the
home.
heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members, that's official.
So before we get started, I have to read this out. So I do not have child protection clearance for Act 153. This is the state law in Pennsylvania. So if anybody here is under the age of 18, you cannot be in this classroom. No, it's not a joke, seriously. I don't think they would have notified me, but just make sure that anybody here who's not 18 or older, it's a Pennsylvania state law and criminal history patch. I don't have the criminal background history or criminal history background to pass this. So again, if you're anybody coming in, if you're under 18, please leave the room. With that aside, I'm going to give a quick shout out to people who's helped us get here where we are today. So this is Easy E in Crooklyn, JL in Seattle, and then DJ Drop Tables unfortunately passed away this summer. So RIP to him. And then DJ Mushu is in lockdown, which is a whole other issue. So we send our respect for him. Okay? All right, so with that out of the way, let's get into databases. So I sort of mentioned this in lecture 0, which I did re-record today. I apologize for the mic, but it should be better now. So as we go along throughout the semester, you will see I get very, very excited about databases. And this is for sort of a very important reason. I only care about 2 things in my life, right? The first thing is my wife and my biological daughter, and then the second thing is databases. I don't care about anything else. I don't talk to my family. They're all Trump supporters, they're anti-vax. I don't care about them. I don't have any hobbies. It's just databases. I live what you call a database-centric lifestyle. And hopefully I hope to impart to you guys what that means, what that entails, and you can continue down the path beyond this course. Now, earlier last week, someone posted this on the CMU Reddit, right? They want to know whether taking 440 or 445 is harder because they want to spend their time doing other things in their life, right? So I chime in and say, whoever this person is should not be taking the course because I don't care whether they think it's hard or easy, right? You will see throughout the semester that if you take a viewpoint of everything is pretty much a database problem, and then all your time should be spending working on databases, then you'll be happier in your life. So again, I don't know if someone's in the class here that posted this, you don't belong. So again, it's quickly a reminder about for the course logistics. Right, everything's on the course web page. All the announcements and discussion for projects, homeworks, logistics, and other things will be done through Piazza. All the homeworks and projects will be submitted through Gradescope and auto-graded. Your final grades for the mid-semester grades and the final grades for all your projects and homeworks will be, and final exams will be posted on Canvas. If you're on the wait list, I think our max capacity is 140 before the fire marshal shows up. And as of an hour or so ago, we have 6 open seats, and the administrators will fill off people from the wait list into that. So if you're still on the wait list, you may have a chance to get in, but I can't guarantee it. Okay? And then if you're not at CMU, we'll make everything available for the projects through this Gradescope. Use this code. Make sure you put yourself as the university's Carnegie Mellon. Everybody in this room right now, do not do this, because then you won't get a grade. And then basically ask everyone else who's not at CMU, who's watching the videos, don't post your solutions on GitHub. Don't do the stupid thing of submitting the PR with your code, because we're going to put a wall of shame up for that. And then don't email myself or the TAs if you're not a CMU student. Everybody else here in the class, please post on Piazza, and we will respond. Any questions or comments about any of these things? Again, if you're coming in, if you're not 18 or older, you have to leave the room because of the Act 153. Okay? All right, so today's agenda, we're going to talk about a quick background of what database systems are. That sort of sets us up for what the course will be about. We'll spend most of our time talking about the relational model and relational algebra. This is going to be the bedrock for how most database systems that you're going to care about, not all, but most systems will be predicated on this. We'll talk a little bit about alternative data models that are out there, like a MongoDBs, document stuff, JSON stuff, and vector databases. But these will sort of be ancillary to what we talk about in this course. The core ideas beyond the relational model of how we're going to build these database-oriented system will be applicable to these other alternative data models. It's just I care less about them, right? Because I care about SQL, I care about the relational data model. And as I said on Piazza yesterday, we'll have, since this comes up every year, people always ask sort of high-level questions about databases throughout the semester. And I want to try to cover as much as I can at the very beginning So if you have any Q&A, if you have any questions you want to ask me at the end, we can take those. Okay? And again, as I said in lecture 0, I get very excited about databases. I talk very fast. Please tell me to stop and slow down. And if you have any questions, please interrupt me and ask me to repeat myself. And I refuse to answer any questions about the lecture at the end of class. I don't line up and say, what did you say in lecture? Slide 5 said this. What do you mean? Right? Interrupt me as we go along, because if you have a question, somebody else also probably has the same question, and so we want to cover these things. Okay? All right. Databases, the second most important thing in my life. Can anybody give me an example of a database? Yes.
ClickHouse.
He said ClickHouse. Anybody else?
A dictionary.
You said a dictionary? Yeah, that's pretty good. What else? Can nobody give me a database?
The contact manager on your phone.
Contact manager phone. Good. Excellent. One more?
IMDb.
Say what? IMDb. Good. Excellent. All right. So he said ClickHouse. He said dictionary. He said contact manager. He said IMDb. So ClickHouse is a database management system. The other examples are all databases. And so what's tricky well, the common semantics of how people describe databases is usually they meant the database systems, which we will focus on in this class. But I want to first sort of discuss what a database is, and then how we're going to build a database management system to manage it. Okay? So a database is going to be an organized collection of data, no surprise there, that are related to way in some manner, and it's meant to model some aspect of the real world. So he said dictionary, and what is a dictionary? A bunch of words, and then their definitions, and maybe like the part of speech or whatever. Right? So that's modeling sort of this, the vocabulary. He said a contact manager. That's modeling someone keeping track of almost a pencil and paper. Here's all my contacts and their phone numbers and email addresses. Right? You're modeling some aspect of the real world, and you're trying to capture all of the constraints and aspects of that real world concept in your database. And again, I'm highly biased because all I care about is databases. But the database is going to be the core concept almost all computer applications and almost all of computer science. At the end of the day, what is a computer doing? Some input comes in, you do something on data, you produce some output. That's a database. That middle part almost always is a database. What is a file system? File system is a database. If you use a website, what are you doing? You're interacting with some form that talks to a database. Right? What is an LLM? It's a database, more or less. Right? So this is the most important thing in computer science. Again, I'm biased, but you're going to encounter databases all throughout your life. And what this class is going to teach you is to understand what a database management system is trying to do for you. Right? Why are things going slow? Why is my query coming back with garbage? Right? So if you understand how the components are implemented, what they're doing, you're in a better position to use a database system, to manage a database. So no matter where you go off and become a database systems internal developer, like all the companies that are coming in a few weeks to talk to us, or you go off and do something else, at the end of the day, you're going to interact with databases, because that's what really life is all about. Everyone's got a smartphone here, right? All those applications are running SQLite. SQLite is a database management system. It's the most widely deployed one, right? So we'll understand how SQLite is actually implemented. And in homework 1, you'll use SQLite. So let's discuss a toy example, and they can use that to explain the various parts of the relational model and database management systems as we go along. So assume we're trying to build a Spotify clone, right? So it's some kind of digital music store, and we want to keep track of the artists that are putting out music, and then the albums that those artists release. Right? We want to know what, for a given album, what artist appears on those albums. So a really simple implementation of the database could just be a bunch of files on disk. Right? In my example here, I'm showing them as CSVs or comma separated values, but it could be JSON. The kids love YAML. You could do YAML. It doesn't matter, right? But we're going to have a separate file per entity. So we'll have a file for the artists, and artists have a name, the year that they came out, and maybe the country that they're located in. And then we'll have albums with the name of the album, the artist that appears in the album, and then the year the album was released. Right? This is a database. I don't recommend doing it this way, but you could do it this way. A bunch of files on disk. So now, anytime you want to update or insert a new record, we just could go open the file, append to the end of it. Or if we need to answer a query, we just scan through it until we find the answer that we want. Right? So say we want to answer a query like, what year did the Jizza go solo? Well, I could write some Python code that just opens the file up, reads every line, parses it as a CSV to get back an array or list of values. I know that I'm trying to look up the name Jizza. Well, the name is the first field in my file, so I just jump to the first element of the array, check to see whether that value equals Jizza. If it does, then I print it out. Right? This is the database system, more or less. Well, this is interacting with the database. That I'm basically embedding the logic of a database system inside my application to do this. Is this a good idea or a bad idea? I guess it says straw man at the top, so you know it's a bad idea. So why is it a bad idea? Yes?
So we kind of need to look over every entry.
So he says you kind of need to look over every entry. Yes. So my example here, my file has 3 lines. OK, well, who cares? Like that'll sit in L1 cache. It'll be super fast. But always, when you think about in computer science, especially in databases, think about what happens if you scale up to really large numbers. So what if my file had 1 billion records? Do I want to be scanning through and parsing every single line just to find the element I'm looking for, one entry? No. What are some other problems? Yes?
You have to rewrite the code every time you want to change your query.
Excellent. So he says you have to rewrite the code every time you want to change your query. Worse than that, what if I want to add a new field, right? Now I got to change a bunch of my code as well as updating the file. That sucks. Maybe one more. In the back, yes?
If you insert a line that's like reordered in a different way.
Yes. So he says, what if you come across a line that's reordered in a different way, right? Maybe like they swap somebody stupid. Again, these are just files on disk. They open up a text editor and flip the order of these things, and now my Python code is going to choke on it, right? Or even like, what if I put instead of the year 1990, I put a phone number in? What happens then? Right. So there's a bunch of problems doing this approach, but this is what the database system is going to prevent you from encountering these issues, because it'll manage all these things for you. So there's some other issues we have to deal with, right? So in my file, I just if an artist puts out multiple albums, then in my album file, I'm just repeating their name over and over again: Wu-Tang Clan, Wu-Tang Clan, Wu-Tang Clan. But how do I make sure that someone doesn't like drop an N in the the name of the Wu-Tang Clan, and now it's Wu-Tang Clan, right? Well, I know that they should be the same thing, but the data says that they're different. We brought this up before. What if someone comes along and overwrites the album name with a weird string, puts an email address in, or puts in a random number that shouldn't be there? And then we didn't talk about this, but in my toy example, I assumed that there was one artist per album. But if it's a mixtape, there's a lot of artists on that. And in my simple example, I couldn't handle that. Then what happens is, what if I delete an artist by accident or by choice from the artist file? But now I got a bunch of albums that mention an artist that doesn't exist in my table or my file. So I basically have a dangling pointer now. We've talked about how on the implementation side, how do you find a particular record? Well, just iterating over a single file and parsing it one by one. That's terrible. That's slow. What if you have another application that wants to use the same database? Well, now I got to basically copy and paste the code that I wrote to parse that file and get records out and put it into my other application. But what if I wrote the first version of the application in Python, but then I rewrote it in Rust? Now I got to translate all the Python code to Rust code. That sucks. But then what if the other application is running on a different machine or a bunch of cell phones? Now I got to make sure that all the application implementations can access that file some way through like a distributed file system, which is the database, by the way. And then what happens if we have 2 threads try to write to the same file at the same time? Well, we could do something really, really stupid and just let the OS lock stuff for us, lock the file, and then prevent only allow one thread to write into it at a time. But a recurring theme you're going to see throughout the semester is in the world of databases, the OS is our frenemy. We never want to let it do anything for us. So letting the OS lock files for us is a bad idea, because we're database people and we can always do it better than they can. So only allowing one thread to write it to the file at a time. That is actually what SQLite does, but SQLite's meant to run on cell phones. If you're running a machine with 1,000 cores, you don't want to do that. And the OS implementation is always going to be more inefficient anyway. And then lastly, what happens if we're modifying the file, and we're going to write a new record. We write half of it, and then it crashes. The machine crashes. Someone trips over the power cord, lightning strikes the transformer, whatever. Now we come back online. What should be in our file? Well, if we just write to the file, we'll just see whatever we wrote before the crash. But that's invalid, right? Now we have a record that's missing half of it. And then what if we want to allow multiple machines to access the file or the database, and we want to make sure that, and if any one of those machines goes down, we can keep running and still serve queries, serve requests. Well, now I got to basically implement a bunch of load balancing stuff to handle accessing the file. That sucks. So this is just a quick smattering of the problems that we're going to have to solve throughout the entire semester to make it so people don't have to do stupid things like relying on the operating system or managing a bunch of stuff in application code. All right, and this is what a database management system is going to do for you. Right? It's going to be the software that allows applications to store, analyze, query data in a database. And a general purpose database system will be one that can support any arbitrary schema, within reason, of course. It can allow any arbitrary queries, meaning it's not hard-coded just to do that one lookup on the JIZA. You can change the query to do any lookup on any artist or any field, or do any kind of transformation. And it's going to do this according to what we'll call a data model. It's a high-level representation of what is in a database, right? And again, just to push this point home further, database systems are some of the most widely deployed and widely tested and vetted pieces of software in the world. That maybe rivals, maybe operating systems is the only one I could think of. Maybe some embedded systems, right? There's multi-billion-dollar corporations that are running off of database systems that are tested and sold by major enterprises. There's a lot of money involved in database, both building them and selling them, and a lot of money riding on a database system operating correctly. And so at no point, say again, if you go off in the real world and you're going to do a startup or whatever, at no point should you say to yourself, oh, I'm just going to build my own database management system in my application. That's a bad idea. You're going to have problems. We're going to rely on these existing tools that are out there. And again, this class is going to teach you how to do it. All right, so a data model is going to be this high-level abstraction that is going to represent data in a database. Again, according to some scheme we'll see in a second. And most database systems support only one data model, like a relational database or a document database. The lines start to get blurred more recently because in relational databases, you can store documents. You can store JSON now in a field. And now the document databases all support SQL and like relational-like things on top of JSON. So in some cases, it's clear that there's a distinction between the data models. But in the more widely deployed systems, again, the lines get blurry. And so given a data model, your database will be defined according to a schema that just specifies, I have these tables or these collections of data. They have these attributes with this name and this data type. Again, we'll see this throughout the entire semester. But it's a way to specify the structure of the things you want to store in your database. Because without a schema, it's just a bunch of random bits, and it doesn't mean anything, right? The schema is going to allow you to provide a structure to the data so that you can write queries against it. Now that I think about this, say I have a bunch of log files from my application server. It's a bunch of text lines, right? With timestamps and so forth. If I don't have any structure on top of that, then there's no way to sort of find the data I'm looking for. But if I say, oh, a log file entry is going to have a timestamp, followed by maybe an event code, followed by a string with the event. Well, that's a schema. That's a structure that I can then run queries on top of it. Because otherwise, again, if it's just a random bunch of bits, the data is useless. The data is meaningless. Yes?
Wait, how does this differentiate with the data model? I thought the data model would also give.
The data model is, we'll see in a second, a data model is the abstraction for how you define collections of data. And then their relationships between other collections. The schema says, okay, within that data model, I have these collections that have these attributes with these types. Think of it like it's almost like a class versus object in like Java world. The class is the definition of the data model, and then the instantiation would be, actually that's a bad example. It would be like in the programming language you would specify like in Java, the Java has a way you define how you represent data, and then you would create instances of it in classes. Let's go further along. I think it's a bad example too, but I think it makes sense when you start seeing differentiations between them. Okay. Other questions? Okay. So I'm going to be highly biased throughout the entire semester. I love the relational data model. I think it's how every database system should be implemented, because the relational model can be contorted, at least the modern version of it, into any possible data model you would care about, except for one. I'll talk about it in a second. So most database systems we're going to talk about this semester, and most database systems that are in the real world that you've heard of, are very likely going to be relational databases. But it's not to say that it's the only one out there. Right? There's these key value stores that are out there, things like RocksDB, LevelDB, Redis is sort of like this, where you sort of have a key and then a value, and that's it. And there's no meaning to the actual value except for what the application puts upon it. So this is typically used for simple applications or caching, like a cookie ID to some payload. Then you have this whole sort of category what falls under the moniker NoSQL, which is ironic now because now they really mean. At the beginning when NoSQL came out, they were like, oh guys, SQL sucks. We're not doing any SQL, NoSQL. Now they say, oh, NoSQL really means not only SQL, right? Because they've seen the light and basically become relational databases. So the document stuff, the JSON databases, is probably the ones that you've heard about the most. Like MongoDB would be a document database. Wide column or column family is a subset of JSON databases. It's like Google Bigtable was this, Cassandra was this. Then you have these array databases, so vectors, matrices, and tensors. Tensors are probably the thing you don't want to store in a relational database because since it's like a multi-dimensional array, it's kind of weird to do that in a relational model. Even though the SQL standard last year just added a multi-dimensional arrays. And then there's these hodgepodge of these ones at the end, hierarchical network semantic entity relationship. I'll talk about network one a little bit from Codicil. But these are like stuff from the 70s and 80s. They were doing cocaine back then. They were experimenting. But basically, the world has come back to realize that the relational model is the right way to go. Every 10 years, though, there's always this repeat where someone says, oh, relational model is stupid, SQL is stupid. We're going to have a new data model. And then everyone gets all excited about that on Hacker News. And then they eventually come around and say, oh, yeah, relational model is the right idea. So right now, we're in the phase where all of these guys have said, oh, yeah, SQL is actually a good idea. And then the next step is going to be the vector databases come back and say SQL is a good idea. But we'll get there. All right, so again, this course is going to be about relational databases. But it's not to say that the things we're talking about can't be applied to the other data models. It's just, most of the systems you encounter are going to be relational. All right, so why does relational model matter, and why am I so keen on it? Well, if you go back to like the 60s and early 70s, there wasn't this sort of plethora of database systems that we have now. There was a small number of them, and it was very difficult to build database applications. Like think of like mainframe days. And so in the early days, one of the first database systems that was built was a thing called IDS, or Integrated Data Store. That was actually built by GE in 1965 or 66. IMS was a hierarchical database built by IBM to manage the Apollo moon mission, like keeping track of all the parts to build the rocket going up. And then part of this IDS work, there was this thing called Codicil, which came out of the COBOL world. I was basically trying to define what the API is, how you would interact with a database. And so back in the day, in the 60s and 70s, computers were very, very expensive, and humans were relatively cheap. The labor of humans were relatively cheap to computers. So it wasn't that big of a deal that people had to spend a lot of time rewriting their code, as he brought up, every time you did make a change to your database, right, if you use these other data models. And that's because there was a tight coupling between, at the logical level, how you're defining your database, and then how the data system actually physically represented it. So now in your application code, you had to be aware of how the database was laid out in the bits on disk, and how things were connected with pointers. And you had to basically traverse those data structures manually in your code, right? And so that meant that anytime there was a change in your database schema, you had to go back and rewrite all your application code to account for that. So an example would be in IMS, at least the early days, you would define a table, and then you would tell the data system, I want to store it either as a hash table or a B tree. And then say if you made a mistake and said, oh, I really want to store it, I decided to do a hash table, but I really need to do range scans, and you can't do range scans on a hash table, and I want to switch it to a B tree. Well, I got to dump the data out, then load it back in as a B tree, then rewrite all my application code because now the API to that table has changed because it went from a hash table to a B tree. So there was this guy at IBM who basically saw all these programmers doing the same thing over again, making all these mundane changes to their database applications every single time there was a change. And there's always going to be changes in databases, right? Because as the world evolves or the data you're capturing evolves, you want to evolve your database. So there's this guy named Ted Codd, who was originally a mathematician. He did his PhD in mathematics. He joins IBM Research in New York. And as I said, he was seeing all these programmers doing the same thing over and over again, just rewriting their applications every single time the layout or schema changed. And he obviously thought that there has to be a better way to do this. And so he devised the relational model in 1969 as a sort of abstraction to a database based on sets, or sorry, based on relations, which I'll explain that in a second, and that there would be this logical connection between data through values rather than physical connections like pointers and offsets and things on disk, as you would have to do in the other data models. So the first paper that defined the relational model came out in 1969. I think this was an internal tech report at IBM. But the one that's really, really famous that everyone refers to is this one here that came out in the CACM in 1970. So if you say, what's the first paper on the relational model, people typically point to this other one here. And so when this came out, all the academics thought this was the greatest thing ever. This is clearly how we should be building database systems. But IBM poo-pooed it or ignored it, right? Because they were making so much money on IMS, which is the hierarchical database system. And then one of their own employees comes along and say, hey, the thing you're making a lot of money on is actually stupid. You don't want to do it this way. You want to do this other way for this system that hasn't actually been implemented. But here's the better way to represent databases. And again, he was a mathematician. He wasn't building a system at the time. And actually, in this first paper here, it's all mathematics. There is no SQL at this time. He didn't define a programming language. It's all through relational algebra and how you manipulate databases. So from IBM's perspective, they were like, well, we can't do anything with this. It's just a paper, right? So, but eventually IBM did do this, did take the paper, but not in New York, actually in San Jose. They got a team together, which we'll cover throughout the semester, and actually build one of the first relational databases as a prototype based on Ted Codd's paper. So I mentioned Codicil. Codicil is a hierarchical database that was spearheaded by the guy that was building IDS or IM at GE. And so there was a sort of back and forth between the relational guys, the people that were like in academia, that were like the relational database is the right way to go, and then all the Codicil people, all the COBOL people said, no, Codicil is the right way to go. And so, actually, who here has ever heard of Codicil? Codicil? No one, right? Because it's dead, right? So Codicil was based on these like sets. So you would define like these collections as if tables, and then you would define the relationships between them through these sets, and you would basically iterate over every element in each set and follow pointers to go find the data that you're looking for. And so there was this famous workshop in 1974 in Michigan where they got all the people from the Codicil camp and all the people from relational database camp, put them in a single room, and they fought over it. So this is a very, very famous meeting. Obviously, Ted Codd was there, but there's been four Turing Awards in databases, and all four of those people were there. And so we're going to cover a bunch of these guys throughout the semester. Bachman was the Codicil guy. He's dead. Jim Gray invented two-phase locking. We'll have a whole lecture on that. He's dead. And then Stonebreaker invented Ingress and Postgres and a bunch of other stuff that you may have heard of before. He's still alive. He's 80. He turns 81 this year. He was my PhD advisor. He's brilliant. But basically, all the Codicil guys are saying, hey, this relational model stuff, you can't actually build a real system doing this, right? People aren't going to understand what it means to have relations and tables. And then furthermore, if you're going to be programming at a high-level language, again, SQL, the guys that invented SQL were actually at this conference too. But at the time, SQL was very early. Like you're never going to be able to take SQL and compile it to a program that can run efficiently, right? So they all complained. The Codicil guy said that relational database is a bad idea. But then the relational guy says, they all say that this codicil thing, these sets that you have to walk through and these records and deal with the physical data structure, that's all a bad idea too. Like it makes the application brittle, makes the application more likely to break when one part of the database breaks. It breaks all the other stuff because it relies on the physical integrity of data, right? And as I said, nobody here has ever heard of codicil. The relational camp won. But again, as I was saying, every 10 years, people forget all the things we've learned before. And now the graph database guys are basically making the same claims now as the codicil people did in the 70s. All right, so what is the relational model? So it's a data model that's going to define a abstraction for a database based on relations to avoid the cost of having to maintain the implicit knowledge of what the data looks like physically in your application code. So there's three key ideas in the relational model. First is that we're going to store our database in as simple data structures, i.e. relations or tables, and that we don't expose that information to the application code, right? You get this abstraction of just, I have tables and I can interact with them. The physical storage, the way the actual database system is going to actually write down the bits of your tables is left up to the implementation. So the idea here is that, say I have a database, I use a database system, I have my database and I store it in a database system that stores things on disk, but maybe I want to store things in memory, in an in-memory database. Well, if I define things through relations and interact it through SQL, in theory, I could take my database out of the disk database and put it into the in-memory database, or some new storage device comes along, I just plop it in that one. And now I don't have to change any of my application code, even though the physical layout of the bits has changed. Now, I say in theory this should work. As we see next class, there is a SQL standard. Nobody follows it exactly. The only sort of de facto SQL standard we have now would be Postgres, because everyone can take the Postgres parser and reuse that. But we'll see many cases where just because I have two relational databases doesn't mean they're always going to be compatible. So again, I say in theory you should be able to do this, but not always. And then at the last one again is that instead of writing procedural code like a low-level for loops to iterate a single one record at a time, as I showed my toy example before, we're going to write queries in some kind of high-level language. And the spoiler is going to be SQL, but we have to do relational algebra first before we get there. And then that way we just say, here's the answer that I want, and it's up to the database management system to figure out what's the most efficient way to implement it, to execute it. Right? So my example before where I said I was parsing that file to try to find one record and said, what if I have a billion records? Then that would really be slow. But if I wrote it as a SQL query and say I had a billion records and things went slow, well, then I can go back and add an index so I can jump to the exact record that I want. Think of like a glossary in a textbook. I can jump to the page I want for some keyword. And then now, I don't have to rewrite my application code because I have an index. Because I've abstracted away the implementation of both the data and the query plan. So we'll see as we go throughout the semester. Again, back in the 70s, people were making the same arguments when C came along, the C programming language, that, there's never going to be a compiler that can generate assembly for C code as well as a human can write. Of course, now we know that's crazy, right? Compilers are very, very efficient. Same thing was said about SQL back in the day from the codicil guys, that no computer program is going to be able to generate a query plan for a SQL query that's as efficient as what a human could write themselves. And of course, again, nobody writes SQL by hand anymore, or at least, sorry, nobody writes the query plans by hand. Let the data system do it for you. All right, so there's going to be sort of three components of the relational model. There's going to be the structure of the database. Again, that's going to be the definition of the tables we have. You can use the term tables and relations interchangeably, but to be pedantic, you would say relations, not tables. Right, you define what's going to be in your relations, and then their contents, and you define this independent of their physical representation. And we'll cover that a bit further next slide. And then you can also define what we'll call sort of integrity constraints, and these are going to be definitions of what the data is allowed to look like in accordance to whatever you're trying to model in the real world. Right? So if you store someone's age in a database, we know no one can be negative. Right? There's nobody that's negative 10 years old. So we can put a constraint in our table, say this value of this age can never be less than 0. And then the last one is going to be the manipulation mechanism, and this is basically the API, the programming interface that is exposed to us to allow us to access and modify the contents in our database. And this is what relational algebra will be that we'll see in a second. But I'm going to cover the independence thing first a little bit more, because it seems obvious now, but again, in the 1970s, this was considered groundbreaking. But the idea of data independence is that, again, we don't want to have to expose necessarily the physical layout of data on whatever storage device we're storing it on to the application, so they can program against it using a high level abstraction. Right? So at the lowest level, there's database storage. I'm not defining what that is, because it could be in memory, it could be an SSD, it could be an object store like S3. Again, for our purposes here, it doesn't matter. And then you would define a physical schema of basically how to represent the database you're trying to store in that database storage device. So this would be defining the pages, the layouts of the pages, like how the bits are actually laid out in a single page, how the files are organized. Is your database one file, multiple directories? All right, what do your extents look like? Are you packing multiple files in multiple pages in a single stent, or is it a single stent per table? All that is handled at the physical schema level. And then above that, you have the logical schema, which is how the application is going to define what's in my database. I have these tables, I have these columns, I have these constraints on them. Typically, we do this through SQL, like a create table command. Then I have a further abstraction on top of that called an external schema. And this is where I can define sort of virtual tables on top of my existing tables. And these are called views. Again, we'll cover this throughout the semester. But the idea here is that, say I have some table of student records, and I want to expose to different applications portions of what's in that table. So say like accounting needs to know your social security number, but they don't need to know your grades. Say it's all in a single table. So I can create a view that says, this application can see the table with these columns, and this application can see the table with these other columns. Even though physically it's the same table, it's just exposed to you in a different way. And above that, at the very top, this is the application code. Right? This is the Python code, JavaScript, whatever, doesn't matter. That's going to interact with our database. So physical independence would be this part here, where I could define my tables and their contents, but I don't care about how they're actually being physically stored. And I have a further level of logical independence, where I could say, I have these logical tables, but then I could sort of recompose them in different ways for different applications or different users, and they don't need to know how things are actually being stored at the logical level right below it. So this physical data independence, this was a big deal, because code cell couldn't do this. In your application code, you had to know how to follow the pointers of the data structures that the data system was storing for you. The relational model says there is no notion of pointers, right? Even though we're going to use pointers to implement our system, but we don't expose that to the application code. Again, it's one of those things where it seems obvious now when you hear it, but back in the day, this was groundbreaking. All right, so let's go a bit more now. What relations look like. So as I said, could use the term relation interchangeably with table, but to be sort of again pedantic to the relational model, we'll call them relations. So a relation is going to be an unordered set of data that contains a relationship of attributes that represent some entity in the world, right? So again, going back to the artist table, one record or one entity would be an artist that exists, like the Wu-Tang Clan, and we would have all the attributes that represent the information or the metadata, or sorry, not the metadata, the attributes of that entity together within a record. And a record we're going to call a tuple. Again, think of it, I don't want to use the term row, because a row applies to a row store. We'll see column stores later on, but a tuple is going to represent some entity or instance of an entity within my relation. And so the original relational model had to define that all the attributes you would have in your in your relation had to be atomic or scalar. You couldn't have lists. You couldn't have like nested documents like JSON. That has since obviously been relaxed in the SQL standard, and most data systems support these things. But back in the 70s, you couldn't do this. We'll also have a special value of null if it's allowed, because we can define that things can't be null in our relations. But this is just a way to say that the value of something is unknown for a given attribute. So you would say again, to be pedantically correct, you would say an n-ary relation, meaning a relation with n attributes, that's more or less equivalent to a table with n columns, right? Again, similar to if you say, oh, what database are you using? I'm using MySQL or Postgres. People know what you mean. So if you say table with these columns, people know what you mean. So a core concept of a relational model is this idea of having a primary key. And a primary key is going to be some set of attributes that uniquely represent one entity within our relation, right? So say, for simplicity, we could say that there's no artist can have the same name. So we could say that's our primary key. Of course, we know that doesn't, that's not correct in the real world. But for our purposes here, we can say, oh yeah, there's the primary key is a name for an artist. So for a given name, like a string, I can jump to one tuple that has that information. So you don't always have to define a primary key. Most relational databases will let you define tables without it. What we'll see later on is underneath the covers, if you don't define a primary key, some systems will actually create one for you. And then even though you may define a primary key, some systems may ignore that, treat that as still like a unique constraint, like the value of the primary key is still unique, but underneath the covers, it maintains its own primary key. So SQLite does this. SQLite has its own incrementing value as the primary key, even though, and it just treats whatever you define as primary key as a unique attribute. So going back here, as I said before, we could use the name as the primary key, but that's bad because obviously artists could have the same name. So to get around this, we could rely on like a synthetic ID, like a number that could represent that given attribute, or sorry, given tuple, right? And they could just be incremented monotonically, 101, 102, 103. So the SQL standard allows you to define what are called identity columns. Again, think of these as like synthetic values that don't really map to things in the real world, but it's going to allow us in our application code to uniquely define where that data is located. SQL standard calls it identity. Postgres and Oracle call these sequences. And as we'll see throughout the semester, MySQL, for whatever reason, does things differently. They call it an auto increment key, right? So it would be this column here. So in addition to the primary keys, we also have foreign keys. And the foreign keys are going to allow us to map some set of attributes from one relation to another relation to define that those things are linked together. And again, this is different from what Codicil did. Codicil would actually have pointers from one record to another record that you would literally follow either through memory or through a disk access to go find the things that it was connected to. But in the relational model, instead we're going to use values to represent those relationships. So say before, remember, we wanted to be able to keep track of all the artists in our album. But if the album only has one artist, well, that's fine because we just stored the single value. But what if I have a mixtape again with multiple artists on it? Now, again, I said you can store arrays as attributes. Ignore that for now. In the true relational model form, you would actually have to store this as a separate cross-reference table that keeps track of, for a given artist ID, what album do they appear on. And so these would be called the foreign keys. So you would have a foreign key from the artist table, the artist ID that points to the record in the artist table, and you have an album ID, it's a foreign key pointing to the album table. And again, it's up to the data system to decide how to make this work efficiently. Typically, there's going to be an index that says for this record here, given lookup on, if I have an album ID, I have to have an index on that ID in the other table. So when I go insert something into this table and I need to quickly check, does this album ID actually exist? I can quickly do that lookup. And these foreign keys are going to allow us to handle constraints or other issues where, like, if now I delete a artist and I want to cascade and remove all their albums, well, I can follow this table to go find all the albums that they belong to and then go make sure I delete things here. Or in some cases, you can prevent you from deleting things. You say, I can't delete a record if I know I have a foreign key reference over here. Basically, the data system is preventing you from shooting yourself in the foot. And you may think, oh, I'm a CMU student. I'm not going to make mistakes. Everybody makes mistakes, right? And so the data system can prevent you from causing a lot of problems. So I sort of mentioned this with the foreign keys, but the idea of constraints. These are a way to define what data is allowed to look like. And that could be either within a single attribute or multiple attributes within a tuple, or what values are allowed to look like across multiple tuples within a table, within a relation. So we said, oh, the artist ID has to be unique because that's the primary key. That's a constraint, right? That's saying that there's only one tuple can have a given artist ID across the entire table. So the most common ones are going to be unique keys and then the foreign key references. The SQL standard from 1992 has this idea of basically global asserts, but I think maybe some systems implement this, but they're rarely used because they're really slow. Because think of like every single time I insert into the table, I got to run this other query to see whether my constraint has been violated or not. So the most common you'll see them is defined in the table itself, right? So if I could say I have a name, it's going to be a varchar, that's a string type, and then not null. The not null part is the constraint that says you can't insert a record with a null name. Another one could be explicit check down here. We could say that the year has to be greater than 1900 because nobody can be born in the 1800s. It's not correct, but in the real world, but like that's the idea of how you could apply different constraints like that. And as I said, you can have these global asserts. There's a create assertion command. You basically put a SQL statement in, and every single time you modify the table, this thing runs. But again, they're super slow. Again, always think big. I have a billion records, and I got to scan to make sure that some constraint is not violated across those billion records. Every single update that table, I got to run that across a billion tuples, and that's bad. All right, so the next thing is the DML. And this is basically the way we're going to manipulate and interact with the database through the relational model. And there's sort of two categories of the DML you could have, a programming language you could have in a database. The first is going to be procedural, where this is basically defining the exact steps you want the data system to execute in order to run your query. And the other one would be non-procedural or declarative, where this is you're specifying the answer you want the data system to compute for you. You don't define how you want to compute it. You just say, but this is just what I want. So for this class here, today's lecture, we're going to focus on this one, because this is going to be relational algebra. And as I said, no data system will expose a relational algebra interface to you, because it's too cumbersome to write it. And again, you're basically defining what the query plan should be. Most systems will support this, a declarative language, and this will be based on what we call relational calculus. For this class, you don't need to know relational calculus, but it's a higher level form of defining operations over the relational model. So if you take the advanced class, or we might do the special topics class in the spring semester on query optimizers, the relational calculus will come up sparingly. But for our purposes here today, in this semester, we only really care about relational algebra. Earlier in versions of this course used to teach relational calculus, but nobody uses that in the real world, unless you're building a query optimizer. All right, so relational algebra is going to be define, so the relational model is going to define 7 primitives. And the idea here is that we can use these to construct any possible query you would want to have on a relational database. Now, not entirely true. Right? Ted Codd's original paper in the 70s defined these seven primitives. It's since been expanded because this doesn't handle things like sorting or aggregations or group bys. But I want to cover the core primitives, and then it's sort of trivial to see how you could extend that to do other things that you want to do in a real system. So we're going to be able to chain these things together to compute more complex queries, but I'm going to go through them each of them one by one. So the most basic operation you can do is a select. And this is basically the first order predicate logic to say, here's how to identify the tuples that I want for a given relation. And it could be what I'll call the base relation, like whatever I defined in my database, I'm going directly at those tables. Or it could be from the output of another relational operator, and that's feeding into my select operator. And so basically, you're going to find predicates that be based on Boolean logic to define what tuples are allowed to set, or what tuples satisfy the constraints you want on the data, and then any tuple that does satisfy is then emitted as output. So say I have a really simple table or relation with 2 attributes, AID and BID. I could define do a select where the predicate is where AID equals A2 against the relation R, and that just matches any record where AID equals A2, right? It's like the where clause in a select statement, if you're familiar with that. And you can combine these things together, conjunctions and disjunctions. So I can say, find me all the tuples from R where AID equals 2 and BID is greater than 102. and it produces that relation as the output. Right? So for me, the way I always remember this is like it's the lowercase sigma symbol, S for sigma, S for select. Easy mnemonic to remember that. So in SQL, which most are going to be writing, it's just the where clause, right? So select star from R, and then have my where clause be the predicate for how I'm filtering tuples. And that's equivalent to defining the select operator here. All right, the next thing we do is projection. And this is where we're defining what the output should look like in terms of what attributes we care about from our input that we want to produce as the output, as well as how to manipulate those attributes in any given way. So again, same relation on R with AID and BID. I could have a projection where I take whatever the input is from this inner relation, or sorry, inner operator here. So here I'm doing a select where AID equals A2, and then I take the output of this inner select and now project it where I take the BID value, or the BID attribute, subtract 100 to it, and then also produce AID as the output. So not only am I selecting what attributes I want, I can change the order of them, I can manipulate them, I can do arithmetic operations, string functions, whatever you want, right? And you're just defining what you want the output to look like from any given input. And that's equivalent to the select operator, the projection clause of a select operator in SQL. So far, so good? So then now we're going to be able to start combining relations together, because again, the idea is that instead of having just one giant relation with every single possible attribute I could have for whatever it is I'm trying to model my database, I'm going to break it up into relations and then combine them together to reconstruct the original form. So I have the union operator, which basically just takes all the attributes from one side and all the attributes on the other side, and just sort of mashes them together into a single relation. In this case here, this operator only works if both the relations you're trying to union have the same attributes, the same types, right? Because you're literally just concatenating, taking R and putting S at the bottom of it, and that's the output. So in SQL, you can do this with there is a union operator where you basically combine the values of two select statements, and again, they have to have the same attributes because you're just concatenating the tuples, combining them into a single output. Of course, if there's a union, there's an intersection, right? An intersection is just taking finding the where. Sorry, back. Yes.
So, yeah, back to the union example. If there is an entry that exists in both of the tables, does it remove?
His question is, for union, if there's a tuple that exists in both tables, will it reuse them? Let me think about this. In the original relational model, no, because it's based on sets. In SQL, the answer is yes. Sorry, other way around. In the relational model, it'll remove duplicates. In SQL, it will keep them. So in SQL, if you do a union, it keeps them. If you put union all, then it removes them. Because by default, they want to be efficient, because it's extra work to find the duplicates. I'll say also, too, this is unordered. So even though I'm showing R followed by S, this is going to be a key thing we see throughout the semester, is the order of the relational model in SQL is undefined. So it's OK for things to end up being maybe inserted into your table, and then when you read them back, they come back in a different order. And this is going to open up a lot of opportunities for us to optimize things in different ways, because we don't have to maintain that order. Now, in some cases, we do want that order. We have to put constraints on top of that to do that. And some systems will always store data in sorted order in some manner. But we'll see examples when we see manipulating or updating the database through transactions, that if we maybe run like a background garbage collector, it could reorder things in any way we want, and we get back things in a different order. So if you care about getting back things in the right order, you define an order by clause in SQL. But again, the original version of the relational model does not have that. So intersection is, again, finding things that are in both. In this case here, I have to have the same attributes. There's only one tuple that matches both of them, A3 and 103, and that produces the output below. Difference is finding all the tuples that appear in the first relation but not in the second relation, right? Again, this is just sort of set theory stuff here, nothing exotic, right? So I can do this again in SQL using the except operator. Again, here I have I produce my output A1 100, 101, A2 102, because those things don't exist in S, but because I have A3 103 also in S, that thing is excluded from my output. All right, so this is basic set theory, but it still doesn't. It's not allowing us to identify the relations that we would, or the relationship or the connections between different relations that we would want. So to do that, we want to do what are called joins. But before we get joins, we have to do a Cartesian product, because that's the basis of how we're going to do joins later on. So Cartesian product is, yes?
For the operations we just covered, do the columns have to be the same?
His question is, for these operations here, do the columns have to be the same? Yes. Joins, we'll see in a second, they don't. For union, intersection, and difference, they have to, yes. All right, so I'm say the easiest, a naive join would be the Cartesian product. We're just taking all the tuples that are in one relation and all the tuples in the other relation and just finding all combinations of them and producing the output, right? So in this case here, if I do the Cartesian product on RNS, I get all of these. For every AID, sorry, where AID is A1 and 101, I then generate all of the, I generate all of these guys here, just mash them together, and that's these. And then I go into the next tuple on this side and get all the A2 102s and then mash them together with that, right? So you may think, why is this a good idea? Why would you ever actually want to do this? Because you're generating a bunch of data that actually doesn't actually match with what's in the real world. This shows up when you do experiments and experimental analysis and sometimes in testing, because you want to get all possible combinations of your inputs. You would do the Cartesian product for that. But more importantly, from a theoretical perspective, this is going to be the basis for how we're going to do joins in the next operator, because what we're going to want to do is find all the, where the AIDs in R match to the AIDs in S's, because we know they're going to be connected in some way based on how we define them in our schema. So you can do this in SQL. There is an explicit cross-join operator or keyword, right? So I can say select star from R, cross-join with S, and that gives you the Cartesian product. Or it's not recommended in the standard, but you can just put, the comma-separated list of the tables, and this will produce the Cartesian product for you, right? But the joins are the important thing that we care about. This is basically finding all the matches from one relation, quoting some value with the given attributes in S. And so unlike in the intersection operator where the schemas of the two relations have to be the same, join doesn't have to be. So implicitly, it's going to look for the name of the column and find the corresponding matching name in the other column when I do a join. So for RNS here, when I do a join on RNS with the join operator, I'll find where the values of AID and BID are the same. And then value just sort of comes along for the ride too, because it was part of the matching tuple, right? So again, you sort of think of this as like you're sort of mashing the two tuples together, then checking to see where things match. Like our AID for R has to match AID for S, and the BID for R has to match the BID for S, and then you throw away the duplicate attributes, right? And then that's your output. Joins are going to see this. We'll have to spend a whole lecture on this. Joins are going to be where data systems are going to spend most of their time in running queries. So this is the thing we're going to try to optimize the most to make them run the fastest. There's a lot of different ways to define joins, a lot of different types of joins. We'll see more next class. And so my example here, where I'm sort of implicitly joining based on having the values be the same, or sorry, the names of the attributes be the same, that's called a natural join. So there's a natural join keyword that's basically going to look up the names of columns and see whether they match, and then do a join against them. I don't recommend doing this because, again, it's implicitly storing it's implicitly figuring out what the join should be based on, and you actually want to define how you want to do your join. So you can either do this with a join clause for RNS, and there's a using keyword. You say what you're doing your lookup on, or you can do the on clause where you explicitly say like AID has to for R has to equal the AID for S, and the BID for R has to equal the BID for S. Right. So the bottom one is probably, if you're writing by hand, is probably what you're going to be doing. This has a little bit more information because you're actually specifying what columns you want to do the join on. And then natural join, again, is not something I recommend. Again, the ANSI SQL standard wants you to explicitly define as much as possible. So that way, if the schema changes or things evolve, it doesn't break your application code. All right, so there's a bunch of other stuff that came along later in the 70s for the relational model. It had to rename columns, had to assign columns to variables, removing duplicates, dealing with aggregations and sorting and division. Again, these all came after Ted Codd's original paper, and most database systems are going to support maybe not division, but everything above. Okay? So that's the crash course, what you need to know for relational algebra, but we'll see how this, as we go along, we should build the query engine of a system that's going to be predicated on these ideas. All right, so as I said before, relational algebra is considered a procedural language. Like, even though it's mathematical notation, but you can kind of easily see how you could implement a system to implement it. Right? One of the complaints about Ted Codd's paper in the 70s was they thought it was too mathematical. I'm not saying that I'm brilliant and I could easily decipher it, but I was surprised when they said that because it's not that esoteric. It's not that hard, right? I think any CS undergrad people should be able to understand it. But it's still defining the steps you want the data system to perform in order to compute your query, right? So I have to say, if I'm going to join R and S, I have to define in what order I want that to happen. So I would say, all right, first my choices are first join R and then S, then do the select on it to filter out the tuples that I want. Or I could do the filter on S first based on the BID, then take whatever the output of that select operator, then do the join against that. And again, there would be pretty dramatically different performance of these two queries based on what the database actually looks like. Again, if R and S only have like 10 tuples, then it's not that big of a deal. But if R and S have billions of tuples, then I definitely want to filter as much as I can out from S before I join it with R. But in relational algebra, there is no concept of allowing things to be reordered. I'm defining exactly what I want to happen. So this is going to lead us to next class, talking about SQL. But a better solution is going to be, say, again, the high-level definition or declaration of the answer that I want in my query, and let the data system figure out what's the best way to perform that. And again, now if I change the physical layout or data structures that are in my database, I don't have to change my query plan, or don't have to change my query if it's defined in SQL. I let the data system figure that out for me. So that's why SQL matters. And again, we'll see this more next class. All right, so as I said, the relational model defined by Ted Codd in the 1970s didn't come with a programming language. SQL was invented by IBM a few years later. Ted Codd eventually proposed his own query language called Alpha, but nobody actually implemented that. And there was actually an early version of SQL called Square, which we'll see next time, which required a keyboard that didn't exist because you had to write things vertically, right? It was a bizarre thing. But SQL basically became the de facto standard that it is now. It wasn't the first one. There was another language called Quell, invented by Stonebreaker from Ingress, which later became Postgres. But there was a bunch of there was other variations of relational query languages. SQL ended up being the dominant one. There is a SQL standard, but again, nobody actually implements that exactly in every system. So the idea is that instead of writing procedural code like this, like doing my lookup in Python code, I'm better off writing SQL. Because now I don't care about how stuff's physically stored. I don't care how the query plan is actually going to execute. I let the data system handle all that for me. So any questions about the relational model? Yes?
When we talked about relational algebra, there was no concept of a key, like a primary key in that situation? Because when we did unions, I didn't understand, like, what if we had two values with the same key?
So his question is, when we talk about relational algebra, we didn't mention primary keys. And that's because you would define that in the schema of, like, here's what my relations look like. The data system could then enforce that the constraint that the primary key has to be unique. But then when it came time to actually run queries, you don't care, like, what the primary key actually is. So I can do joins, I can do intersections, all that, without worrying about what the primary key is. Likewise, I didn't have to find what the foreign key was. Right? It's there. It's It's integrity constraint. All right, so I want to briefly talk about, in the last 5 minutes, the leading alternative, which is going to be the document JSON model, and then the vector database stuff is the hot thing now. I just want to expose you to this real quickly, what these ideas are, and then we can mostly ignore them throughout the rest of the semester. All right, the document data model is, just think JSON, right, or XML, or object-oriented, data. Right, but the idea is that you're going to have some kind of hierarchical collection of data where there's going to be these named key value pairs, but then within a given document, you can have a nesting of arrays, nesting of other documents, and so forth. Right? JSON is how you would implement this today. There's older systems from XML, and then even earlier than that, in the early 90s, late 80s, when object-oriented programming was a big thing, there was these object-oriented databases that you've never heard of. That basically try to map like C++ objects into objects in a database. So instead of operating on relations, you would operate on objects. So we'll see this more next class, but the problem that they're trying to solve is this idea of the relational object impedance mismatch, meaning I'm writing code in my application based on objects that have this hierarchical structure, but then when I have to store it in my database, the database requires me to store it as relations, and then now I need a way to map that back and forth between relations and objects, which can be cumbersome. There's a bunch of systems out there that implement this, the document model. MongoDB is probably the most famous one. CouchDB or Couchbase is probably the second one. But again, this idea goes back to the 1980s. So going back to my example of our music store, I would have a relation for artists, I would have a relation for album, and then I have this cross-reference table, cross-reference relation that maps artists to albums, right? So now if I want to get, for a given artist, all the albums that they appear on, I have to do a join to go from the artist table to then the artist album table and then to the album table. So the document model people say, this is stupid, joins are slow, you want to get rid of this thing, and instead what you want to do is just embed, for a given artist, all the albums that they appear on. Or the reverse of that, for a given album, all the artists that appear on it. So the idea is like if you're writing a bunch of Python code or Java code or whatever, you define these classes, and then when now you actually want to store it in your database, in this case here, for a given artist, we're now going to embed the list of albums that they appear on. So now, again, when I want to do that lookup for a given artist, go give me all their albums, it's one query to go fetch that artist record, and then it pulls down all their albums. Is this a good idea or a bad idea? Again, it's obvious what my answer is going to be. Why is it a bad idea? Yes? He says you can't query directly on albums. You could. You can do you can do nesting inside to get things. Yes. She said yes. She said, and she's correct. This is you have to predict what the queries are going to want to look up on, and then model that in your database. Absolutely yes. And then likewise, I'm going to be end up duplicating a bunch of information. If a artist appears on, if multiple artists appear on one album, I got to re-record that over and over again. So in some cases this nesting makes sense. In many cases it doesn't. Yes.
And also, if you want to delete an album, you just can't do it.
And he said if you got to delete an album, they got to find all the artists where the album appears on. Yes. You could do an index. An index could help find that, but still it's implicitly in your application what the layout is. So in some cases you do want to store things as JSON in your database, but oftentimes you do not. All right, so the last one to talk about is vector databases. So this is the hot thing now. There's a bunch of companies that have gotten a lot of money that are building systems in the space. Weaviate is coming to talk with us on campus in a few weeks. I like those guys. They're good people. But no, they're fun. I was on their podcast. They're fun. So a vector database at its core, when you say I have a vector database, they really mean a document database that also has this extra data type called a vector, an embedding. And think of that as it's a large array of floating point numbers. And what they're trying to provide is the ability to do approximate nearest neighbor searches based on these vectors, because these vectors are going to be generated from some kind of transformer, it's an embedding that's trying to represent what's actually in the data you're storing, right? At the end of the day, there's just a fast index to do approximate nearest neighbor search. So what does that look like? So again, say I have my album table, and then somehow I'm going to get out all the lyrics from these albums from Rap Genius or whatever, right? And then I'm going to feed that into some kind of transformer. Either I'm using OpenAI or something from Hugging Face, and then that's going to generate me a bunch of these embeddings, which is just arrays of floating point numbers, and that somehow the magic of the transformer is that somehow implicitly the information or the semantics of the data that I fed into the transformer is in those floating point numbers. So then I'm going to store that in my vector database. It's going to have a vector index. The most common one is HNSW, hierarchical navigatable small worlds. IVF flat is another one, but there's a bunch of libraries like MetaFast or Spotify Noi. But it's going to be some data structure we'll cover in a few lectures to easily do these nearest neighbor searches on these embeddings. So now my query, instead of doing exact lookups like find me Jizza's albums, I can say things like find me albums that are similar to Liquid Swords. And somehow, assuming I have lyrics to Liquid Swords, I can convert that information into, put that into my transformer. I get out the same kind of embedding that I would get when I first loaded my database, and then I do a nearest neighbor search on the vector index, and that returns back a ranked list of matches, right? So the vector database is essentially this part here. They can also store metadata, like they also store this information that I have over here as JSON, right? So I can say, find me all the albums that sound like Liquid Swords that came out after 2012 or something, and I can incorporate that in my lookup. But at its core, a vector database is this vector index piece here. But in the last year or so, pretty much all the relational databases now support vector indexes, right? So it's I argued, and I've told the Weaviate guys this directly, like it's not, the idea of vector search and nearest neighbor search does not mean you have to build a whole new system that throws away everything we talk about the entire semester. It's just an extra thing we can add, and the relational model can accommodate it. So the SQL standard does not support, or doesn't have a notion of this nearest neighbor searches. Postgres through PG Vector has their own API. Oracle has copied that. I think that's going to end up in the SQL standard in a few years. And the vector guys will have to figure out how to overcome that. Okay? All right, this is the crash course in vector databases in 2 minutes. But the Weaviate guys will come talk about it more later in the semester. All right, so with everything, databases are ubiquitous. Databases are important. Databases are the second love of my life. Relational algebra is going to be the foundation for how we're going to build our systems to support them. And then we're going to see this over and over again. We talk about query optimization, query execution. And certainly we'll see this next class when we talk about SQL. Okay? So next class will be, not done yet, Q&A. Next class we're going to do modern SQL. So by modern SQL, I mean like I'm not going to teach you what a select star is. It's 2024. You guys are CMU students. I'm assuming most of you have seen SQL before in some form, the basic form of it. So I'll try to teach you the more advanced things and where things break in the SQL standard. Okay? So at least make sure you understand basic SQL for showing up next class. Okay? All right. We have 8 minutes left. Any questions about databases? Yes?
So you talked about this a little bit earlier. We talked about like the blurry lines between relational and document-based. So like I've used DynamoDB a little bit.
Yes.
And like it feels like you're using a relational database.
They support SQL now, right?
Log on to it. So like how, can you explain like that merging a little bit more and like what that means?
So his question is, he's used DynamoDB. DynamoDB is one of the, from Amazon, one of the first NoSQL databases. It originally started off as, I think, as a key value store. Then they added support for JSON. And then more recently, they've added basically looks like tables. And I don't think it's directly SQL. I think it's part of QL. It's no, not GraphQL. There's part of QL, which is Amazon's dialect of SQL, and it looks like SQL. So why is this convergence between the NoSQL guys and the relational world? Well, because all the things we talked about today are why having a relational model and making sure you can't shoot yourself in the foot in your database is a good idea. They've come to realize, oh, customers actually want these things, and they've added it on top of it, right? So that's why I think there's a convergence, because like in the same way that no one's going to invent a new mathematics where like because 1 + 1 = 2 is just true. I think like the relational model is just the true way, the correct way to implement, to represent data. And you can add accoutrements like the vector indexes on top of that, or the various things that deal with JSON. But everyone's basically coming back around, like the relational model is the right way to go. Terracotta is a genius. Yes?
So I have a question about the vector database.
Yes?
Actually, know this is a very famous startup called Rockset. They recently got acquired by OpenAI.
Yes.
I wonder, like, for this kind of real-time vector search database, what kind of realistic, applications you can imagine, like,
For vector indexes? For your databases?
for like using a vector database?
All right, so his first question he started off is, OpenAI made a major acquisition this summer. They bought Rockset. Rockset was a database startup, a relational database startup, based on the guys that created RocksDB out of Facebook. And OpenAI, he paid a lot of money for it. And so his question is, well, first of all, what is OpenAI going to do with Rockset? I can't tell you. But what are some uses for a vector database? So going back to my example here, right? This idea of this semantic search, like find me the albums that are similar to Liquid Swords. I'm not defining what it means to be similar, right? Or find me the albums where they talk about slinging rocks. Well, you could have your transformer know that slinging rocks means dealing drugs, and even though you ask for slinging rocks, it knows, it somehow magically knows, because the training data it's based on, can how to match that to different things. So it's a way to do better searching based on the semantics rather than finding exact matches. That's what these things are being used for. Yes?
Are we not able to do like these kind of semantic or like fuzzy search through a relational database?
The question is, are we not able to do these semantic searches in the relational database? No, I said absolutely, yes, you can. Assuming you can store an embedding and then have a vector index to do the fast approximate nearest neighbor search, you could write SQL queries against this. Postgres does this with PG vector. Almost all relational databases have now some form of a vector index. You can do this. Prior to this, though, the way you would do lookups would be like fuzzy matching. Like find me all the albums that have the word swords in it, right? But you couldn't do this semantic meaning that's the part that's new. In the back, yes.
If every query needs to go through a forward path through transform, would that be very slow?
His question is, if every record needs to go through a transformer, wouldn't that be slow? Yes. I mean, milliseconds. It takes milliseconds. Yeah, it's not seconds. Yeah.
So it's slower than like a relational database.
Again, be very clear here. Like, you can put this in a relational database, right? The question would be, is running it through the transformer to get back the embedding that then do the lookup, is that going to be slower than doing an inverted index, which we'll cover later on? Maybe. Depends on what this is. Depends on what's in memory. There's so many different factors involved. It's hard to say. And then that assumes that you're going to get the data you would want using a fuzzy search anyway. Again, for some things, like, it's not going to work because there's no understanding of what actually is in the data, what it means. That's what the transformer does for you. Yes.
When we are taking interviews, sometimes the interviewer asks us to design a system, and they want us to choose which kind of database, like SQL or NoSQL. Sometimes they are more satisfied with you when you're choosing NoSQL. But as you said,
well, fuck him if he did that, right? So his question is, sometimes in the job interview, the interviewer will ask you, pick a database for whatever like prototype system you're building. The answer is Postgres. Always pick Postgres, right? I'm dead serious, right? And you can't say, oh, because Andy said so, but like, Postgres is a rock-solid database system that has a lot of the features you would see in a sort of enterprise-y system. And actually, not just for interviews, for anybody doing a startup, anything like that, your first choice would be Postgres, right? Because you want to be spending your time like building your application, not worrying about what database system you want to build. So you can just say Postgres because I want to spend my time building the application because that's what matters. Like no one's going to know or care that your application is running on Postgres versus MongoDB because they don't interact with the database at that level. Postgres is almost always the right choice. Now, you may get to the point where Postgres can't scale and handle your data, and at which point you pay, not me, but pay somebody else a lot of money to help figure out what database, how to make Postgres scale. In the back, yes? Can you speak up? Sorry.
Yeah, so as a career-wise, like, what do you think, like, what are the good companies where you can work, like, it's a good place to work, and where you think, like, okay, we should run away as soon as possible from there?
His question is, what are some good database companies to work at? What are some bad database companies to work at? All right, so good database companies. this is the great thing about databases. There's a lot of money, and there's a lot of people building database systems. So like say you're in operating systems. Where can you go to build an operating system? IBM, Red Hat, maybe, right? The Linux guys are all doing their various things, but like there aren't a lot of competing operating systems. There's a ton of databases, and if you want to go to a big company like Microsoft, the Amazons, the Googles, even the Facebooks, right? All of them are building database systems, and then there's a bunch of startups that are all in this space as well. Now, some of them have questionable financial footings. Well, I say this because my database startup failed this summer, but there's a lot of choices in databases. There's a lot of money in it, right? Even now, even though the relational databases are 50 years old, there's still people trying to build new systems all the time. Now, in terms of bad companies, I'll just say off the bat, Enterprise DB. Them. So avoid Enterprise DB. In terms of other ones, for startups, obviously you want to talk to people and see what the finances look like. You can maybe get a sense of how much they're chasing fads. Like if they're if all of a sudden they start off being some kind of database and now they're a vector database because it's the hot thing, or the AI database, then that looks a little dicey, right? Another interesting avenue is also, I mentioned like Google and Amazon, they'll sell they sell database services. Then there's companies like, I can't say, well, I'll bleep it out. Like they're building a database system. And like the great thing about it is they're building it in-house. They don't have to worry about getting customers because they're their own customer, but they're actually building a whole system from scratch and doing some really interesting things. So there's so many different options to do this in databases. And that's why I think this class is super important, because you're going to encounter this throughout your life. And the companies don't want to hire a bunch of random JavaScript programmers because those people are going to break your database system. You don't want them to touch the internals. They want CMU students who know how to handle these things and are dying to hire you guys. Yes, quick.
Do you think this class is a good preparation for a database career?
His question is this class good preparation for a database career? I am biased because it's my class. I've been told by certain database companies this class is the onboarding process for database companies. I've also been told that the interviews for some database companies are basically entire lectures from this class. So take that to mean what it means, right? There's always money in databases. How about that? Okay? Last question.
What's the best way to incorporate blockchain into my database?
All right, do you have a real question?
What happened to the DJ in this course?
All right. Yeah, so unfortunately, we cannot have a DJ this year because of legal problems dealing with Warner Hall. So I apologize. There is the moral turpitude. I have tenure, but there is the moral turpitude clause at CMU where I can still get fired. So I'm trying to lay low this year. So I apologize. Okay. All right. All right, guys. That's it. See you on Tuesday or Wednesday.
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create, rotate at a rate too quick to duplicate. Feel a breeze at a skate. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil. I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with third-degree burn from one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with St. Ides.